broadcast is now starting. All attendees are in listen-only mode.
Hello, this is Christine Perret. I'm the chair of the Area Research Committee, and it's my pleasure to host today's webinar. This Research Committee webinar is about the ILLIXR Consortium and an exciting project that I hope you'll have an opportunity to learn about and perhaps have the results to benefit you and your company. So I'm having a little trouble. It says that I'm not able to record. So it says it's being recorded now. I'll go ahead and continue. So today I'll be giving you a short overview about the area, and then Professor Sarita Adve will be presenting, and we'll have some time afterwards for questions. If you have questions, please use the GoToWebinar question panel. You are in listen-only mode, and I will read the questions for us in the final stage. So for those of you who may not be familiar with the area, the AR for Enterprise Alliance, we're an industry consortium composing ourselves of three segments. And we believe these are the three important segments of the enterprise AR ecosystem. And we're seeking to support the interaction and the growth of all three of these segments. Most of that growth, of course, needs to be led by the top circle in this pyramid, the enterprises. The enterprise and industrial use cases for AR are very compelling and will have many benefits. So the other two segments, the providers of technologies and services and the non-commercial entities of the ecosystem, are supporting the adoption by the enterprises. And we want to foster the development of complementary existence of these three segments. So how do we do that? We provide thought leadership content. We curate, develop our own, and then share a lot of content, both member-exclusive content and public content. We do this through webinars like today, as well as our website, our social media channels, podcasts, and other formats. For our members, as well as for the ecosystem, we provide networking and a place for the community to collaborate or share experiences on an ongoing basis. Furthermore, we like to support programs that train professionals in the needs of enterprise AR. And the reason is because there's a very important skills gap. And in part, I hope that University of Illinois and what we'll be hearing about today adds to those skills professionals, those people who have very, very strong tools and skills to fill the job positions in customer enterprises. And finally, we have committees, of which the research committee is one, that focus on specific barriers to adoption. And we collaborate within these different committees to provide information and develop other programs. And we're very pleased to have you here today. It's now my pleasure to turn it over to Dr. Adve and to hear more about the ILLIXR Consortium. So, Sarita, are you ready for me to make you presenter?
Yes.
All right, there you go. Perfect. I see your screen. Thank you.
Great. Thank you, Christine. Welcome everybody. My name is Sarita Adve. I'm a professor at the University of Illinois at Urbana-Champaign. And my background is in research in hardware and computer systems. And recently, we've been working on systems for extended reality. So I'm here to tell you about ILLIXR, which stands for the Illinois Extended Reality Testbed, and our consortium is an effort to provide an open source testbed to democratize extended reality research, development, and benchmarking. So we all know in this group, I don't have to convince you that extended reality is likely going to be the next major computing interface. And by extended reality or XR, I include virtual, augmented, and mixed reality. And these technologies will transform science, medicine, education, and virtually every activity that we undertake. But from a systems point of view, there's still an orders of magnitude gap in power, performance, and quality of experience between current and desired systems. So here are some examples. If we want a fully immersive experience where we're wearing lightweight glasses, walking around all day, and really want to experience the full power of mixed reality, AR, VR, etc., the desired resolution is about 200 megapixels. But today's systems, the state-of-the-art systems, provide up to about 7 megapixels of resolution. Similarly, today's systems, the state-of-the-art, the power dissipation is about 7 watts. But if I want to walk around with my AR glasses all day long, 7 watts is just too much. What I want to be in the envelope of about 100 milliwatts. For weight, today the current systems are about 500 grams, but what I would like for a comfortable experience is about 10 grams, and so on. So we have a paper that describes this discrepancy in terms of other metrics as well. So this is a huge challenge. How do you bridge this orders of magnitude gap in power, performance, and quality of experience? At the same time, this is a great opportunity for systems research like myself. But to do research in this area, there's many more challenges. So the first one is that we need a diverse expertise of people to solve the problems that arise in this domain. This domain requires expertise in graphics, in vision, audio, video, optics, haptics, and it's truly an interdisciplinary domain. Furthermore, for the sorts of gaps that we want to bridge, it is quite clear that we need cross-layer system co-design, meaning we want to bring to bear communities that work in hardware, in compilers, in operating systems, in algorithms, applications, and work together to create the systems that we desire. Another big challenge is that the metrics of goodness for these systems are very complex. We have multiple user-driven, end-to-end quality of experience-related metrics. The metrics themselves are a source of, are subject of research today. We don't yet know what are good metrics to evaluate these systems, and their complexity means the design of the system is also complex. And finally, when we started this project, this entire domain, all of XR was dominated by closed systems and very few participants. So even though we wanted to do research in XR, there were no open reference systems or benchmarks for us to drive our research. So there's a large barrier to entry for open research and development for extended reality systems. And that's where the ILLIXR work began. So we realized that the first most important contribution that we could make was to find ways by which we could democratize XR systems research, development, and benchmarking. And this led to ILLIXR, the Illinois Extended Reality Testbed. So ILLIXR today is an open source full system XR testbed. It has state-of-the-art XR components with a modular runtime. It's OpenXR compatible, And we have provided an extensive characterization of the Elixir system, and it is being used for a large number of research projects. So before I tell you more about Elixir and the consortium, I just want to play some demos to show you that Elixir is, it's real. Here are some videos, and these focus mostly on VR, but Elixir also has AR and can be we can use it interchangeably, and you will see that as I give you more details. So here is just a basic demo of how you might use Elixir if you are a researcher or systems designer trying to debug your system, wanting to add new components. Here is my student in this window, and by the way, I don't know how the video is showing on your end, but on my end it's very smooth. Elixir tracking works very well. So if the internet is messing this up, my apologies. So here in this window here where my pointer is pointing, you can my student is walking around with the camera in our lab, and this is the physical space that he's traversing. The larger window here is the virtual space he's traversing. You see the headset position that is shown for the student who's sitting on the desktop to see what is going on in the system. And then on this window here you have the pixels that Elixir is putting out. So this is the Elixir display. Okay, and here we have a debugging window that tells you everything that's going on in the system. We have a lot of telemetry, so you can see what's happening. So this is just a basic functional configuration of the system that you can use to do day-to-day research, development, benchmarking, understanding how to use it, etc. But then if you want to get a full experience, so again, this is a VR experience, you can walk, here's my student walking around with a headset. This is a North Star headset. It's an open source headset, and Elixir is being used to send pixels for display to this headset. So Elixir is running on this, a very innovative chair trolley system, where we have a big PC with a big GPU, and another student is helping to push that PC around so that this student here can see, have a VR experience. And what you're seeing on the right is exactly what the student is seeing through the headset. And you can see that that Elixir tracks pretty well. It has that he's getting a pretty good experience. Now, the reason that he's pushing a PC is because today's commodity hardware that we could run Elixir on is there's, again, as I was saying, there's a huge gap between power, performance, etc. So we do run on embedded systems as well, but on embedded systems you would not get a similar experience, and our research is all about how to bridge that gap. So this was this needed a student to push him around. And Elixir could run on any system, on any PC that you could accommodate in this way. But we've also ported Elixir to a laptop, a backpack PC. HP makes these, and now you have Elixir running on this backpack, pushing pixels to this display, and you don't need any help. The student is just walking around and enjoying an experience. And the key thing to note here is that this entire system is open source, end-to-end open source. You can change it, you can understand it, you can measure it. It has a lot of telemetry. You can measure pretty much anything you like, and I'll show some of that to you later, and improve it in whatever way you like. Okay, so essentially we have succeeded in providing an open source testbed for people to use. So this is quite a bit of advance since when we started, but there's a long way to go, and we don't think we can do this ourselves, of course. So we launched the ILLIXR Consortium recently. This has several industry and academic partners, for example, ARM, Facebook, or Meta, Micron, Northstar, NVIDIA, etc., are part of our consortium, and the list is growing as we speak. The goals of the consortium are to use Elixir as a foundation to develop a reference open source testbed with reference components and interfaces, a modular and extensible runtime system, and a telemetry that everyone can agree on. And second, to develop a common benchmarking methodology. Today, there's no standard way by which we can compare different headsets and different XR experiences. We would like to develop a common methodology, including applications, data sets, system configurations. As you know, you can play an XR system in various configurations with different power and quality of experience trade-offs, and the metrics. How do we judge the goodness of these systems? And finally, to build an XR systems research and development community. So as you know, this community is very fragmented, and we would like to get these groups together. So this is, Elixir has been recently funded by a U.S. National Science Foundation Community Research Infrastructure Program as well. So we are delighted to get this backing as well. And I will tell you more details as we go along, but if you'd like to join us, you can either send an email at the address here, elixir@cs.illinois.edu, go to elixir.org. There are various ways to contact us and get involved there. We have a Discord that you can join. And in January, we will be restarting our open weekly meetings, and I'll say more about that later. Okay, so what is Elixir? What exactly does it look like? What does it do? That's going to be my next part. Before I go ahead, I want to acknowledge the large team of people that has contributed to Elixir. Have some amazing students who've contributed to Elixir, and we've also consulted externally with several people in industry and academia to help us build this system. So thank you to all of these. And then I want to highlight Huzaifa Muhammad, who is my senior grad student who has led Elixir from the beginning. And he would have been given this presentation, except that he is he is sick at the moment. Okay. So here I have an overview of Elixir. This is a standard set of components you would find in an XR headset. You have the XR applications that run on the headset, which the speech box is what comprises Elixir, and this box runs on a mobile device. So the standard sort of XR system consists of three subcomponents or three pipelines. The perception pipeline, which tells the user which tells the system where the user is and what the world around them looks like. The visual pipeline that works with the perceptual pipeline to send pixels, to generate the pixels that will be displayed, and the audio pipeline that does the that provides audio to the system. So I will be talking about each of these in a little bit more detail, not too much detail because of time, just to give you a sense of what Elixir contains. But these three things are not independent. They all coordinate with each other, and this coordination and orchestration is done through the Elixir communication interface and runtime. And I will talk about this runtime as well. And then the applications, the high-level applications, games, education, virtual tours, or enterprise applications, they run on top of all this. And the interface that we are very excited about, that is now an open interface. This didn't exist when we started. This is the OpenXR interface, and Elixir is compliant with OpenXR. I'll talk a little bit more about that later. So if your application is OpenXR compliant, it can work directly on Elixir, and if not, then we do have a separate direct way to reach to work with Elixir as well. Okay, so just quickly, what do we support in the perception pipeline? Again, around the user and where the user is in the world. So we support several sensors like cameras and inertial measurement units. We have a component for visual inertial odometry, which provides position and head orientation or the pose. And you will see that we can deploy several different algorithms to do this. We have an IMU or inertial measurement unit integrator that provides high frequency pose estimates. So the VIO or visual inertial odometry that I just talked about works at a lower frequency. It's a much more complex piece of software. The IMU integrator provides higher frequency pose estimates, which may be less accurate. Or it takes high frequency pose estimates from the IMU and then integrates with the VIO to provide more accurate high frequency pose estimates. There's a pose predictor that extrapolates the pose to a future timestamp. You will see why we need to extrapolate to the future in just a bit. And then there's scene reconstruction that uses RGB and depth cameras to build a dense 3D map of the world. There's eye tracking that tracks where the eye is to feed downstream into Elixir. The visual pipeline consists of asynchronous reprojection. This is meant to reduce the motion to photon latency in the system. The idea is to warp the rendered frame to account for the head movement during rendering. So the renderer grabs the pose from Elixir's VIO, but from the time that it grabs the pose to the time that the rendered frame will be displayed, the user's head may have moved, and so reprojection accounts for that movement using the latest pose estimate and a prediction for the future when the frame will actually be displayed. So this cuts down the motion to photon latency considerably and gives a much nicer user experience. We also have techniques to do lens distortion and chromatic aberration correction to correct for distortion due to curved lenses. And we also have support for computational holography to provide for computational displays with multiple focal planes. For the audio pipeline, we do 3D spatial audio encoding and decoding. We use multiple sound sources, encode them into high order ambisonic sound field. And then for playback, we play back based on the user's latest pose so that you have a nice 3D localized sound experience. Okay, so that's the components that the Elixir currently supports. But XR is not just a collection of components; it's an entire system, and the system data flow, as you know, is pretty complex. So you have the IMU running at a very high frequency, you have the camera running at a lower frequency, you have the IMU and the camera feeding to the VIO and the IMU feed to the IMU integrator. There's eye tracking, scene reconstruction is using the camera, the scene reconstruction IMU eye tracking feed to the application, reprojection is dealing with these components, then there's the hologram, audio encoding, decoding, etc. And so there's many different components in the system running at different frequencies with multiple interacting pipelines, synchronous and asynchronous dependencies, and multiple quality of experience metrics. So this is a fairly complex system, and our runtime, we built the Elixir runtime from scratch to orchestrate all of this work. One thing that we've kept, we've been very, very careful about from the get-go is to have the runtime be extremely modular and provide a flexible architecture, because the goal from the beginning has been to provide a usable testbed for others to experiment with. So in our runtime, the Elixir components are plugins. They can be separately compiled so that you can do the development independently, dynamically loaded, and you can easily swap and add new components to Elixir, new implementations. In fact, we have multiple implementations of many of these components. But at the same time, we didn't want modularity at the expense of efficiency. So we put in a lot of effort to make sure that this is an efficient and flexible system. Our communication interface is designed for that. The communication interface is based on a publish-subscribe model that is common to many such systems. Each component specifies event streams that it wants to publish or subscribe to. It specifies the synchronous or asynchronous consumers. For efficiency, we use copy-free shared memory implementation. So unlike many of the off-the-shelf runtime systems, we use shared memory, and this provides us with a high level of efficiency. So again, the end-to-end system balances flexibility with efficiency. As far as applications, again, as I said, we can write XR applications directly to Elixir if that's what you prefer. That the Elixir room that I showed in the beginning was written directly to Elixir, or we can use OpenXR applications. And we're very fortunate that the Monado group has an open implementation of the OpenXR interface. So we use that, and in fact, Elixir is a device, official device of Monado, and supported by Monado. So today, Elixir runs on Linux, and so we run Linux applications for game engines. There's a Linux open source game engine called Godot that supports many applications which we can run on Elixir, and soon we will have Unity and Unreal's Linux OpenXR implementation running on Elixir as well. These have just come out, are going to be coming out soon. Okay, so as far as the end-to-end quality metrics go, we measure motion to photon latency. This is the time from the head motion to display. This is a critical quality of experience metric in an XR system. We can measure the image quality that is displayed using standard metrics like SSIM and FLIP. Again, there's lots of research to be done on what are appropriate metrics. We provide extensive telemetry, as I said, frame rates, missed frames, time distributions, power, etc., to understand what is going on in the system and how the system can be improved. And then these are the components that we support in Elixir. Today, this is a growing list. As you can see, there are multiple versions for various components. This is by no means a complete set. There are several we have internally that we are in the process of integrating. So that was about Elixir. I want to tell you a little bit about what we've done with Elixir. First, I'll talk about the evaluation and system implications. Since I come from a systems background, components here. As we know, to use an XR system requires significant amount of tuning in the system. So we did that. This itself is a research problem. How do you tune the system to get the best possible experience for the given application, for the given user, etc. So far, we've done hand tuning, but this is again a research problem that we're working on to do this automatically. We run Elixir on high-end desktop machine that you saw my student rolling around, as well as embedded class machines like NVIDIA Jetson H, which we run in a high-performance mode and a low-power mode. So the high-end desktop machine gives us, in a sense, the sort of upper bound for where systems are today, that and how well they will perform with something like Elixir. And the embedded class machine tells us, so the high-end machine, of course, uses a lot of power. It's not something you would use to build a headset. The embedded class machines, especially the low power mode, gives us a bound on what we can do with the low power machines of today. For applications, we looked at various applications that cover a graphics intensity from high graphics intensity to low graphics intensity. So I don't have time to go through all the results, but I just wanted to summarize. We've done a lot of measurements to see how well the systems behave on the desktop, on the Jetson HP configuration, on the Jetson LP configuration, for each of the different subcomponents, like the camera subcomponent of the perception pipeline, the IMU subcomponent of perception pipeline, visual part of the system, the audio part of the system, etc. Using different applications. So, I talked about the 4 applications. Those are the different colors in the different bars. So you don't need to, look at these results in detail. That's a whole another talk. But suffice to say that we can collect. We've measured the frame rates and got insights about what the implications are for system design. We've been able to measure execution times and distributions of the execution times per frame, seen a lot of variability in these execution times. We can figure out where the time is going, which component of the system is using more of the CPU or GPU power, so that we can improve the system, improve the application, so that it can exploit the system better. See where power is being drawn, which aspects of the system, again, is it in the CPU, the GPU, the display? Is it the VIO that's drawing power? Is it the application? So that we can then improve the system. And then what is the quality of experience? So looking at what the motion to photon latency is, what is the image quality, etc. These are the first published performance, power, and quality of experience results for an end-to-end XR system to our knowledge. And the paper was it's published in ISWC and referenced earlier in the talk. So what are the implications of these results, right? So it's great to see these results, but what do they really mean? These results point to many different, they are providing us with a blueprint for the research we want to do as systems designers, and also for those developing applications and algorithms for what is important in moving forward to make these systems work as we desire. So the first thing is, yes, we confirmed that there is a substantial performance, power, and quality of experience gap in these systems, and so we need to specialize the hardware and the software and the system as opposed to using general purpose components. We do need to specialize hardware, build accelerators, and that's a big part of my own research agenda. As well as for software, design specialized software stacks for these specialized hardware accelerators and specialize the entire system. The other interesting point we found was that there's no application component that dominates all the metrics. So it's not like as if SLAM or VIO is the most important thing, or rendering is most important. These may be most important from a performance point of view, but from a quality of experience point of view, there are other components that may be more important. And so we need to consider all application components in the system together. Going back to that whole concept of this needs to be a cross-layer, cross-disciplinary effort to build systems along with the applications, so that we achieve the goals that we want. For people like me, we are concerned a lot about power, and so one thing we noticed was that power consumption goes beyond the traditional CPU, GPU, and memory components. We need to consider system-level hardware components such as displays and IOs. There's very significant variability in the system, so there's need to partition, allocate, and schedule system resources. And finally, the per component metrics do not capture QoE. We need to look at the entire system to make quality of experience driven trade-offs. So in summary, what this is saying to us again is what I started with, that this is really not a problem that can be addressed in individual silos where the hardware people are doing their thing, the runtime people are doing their thing, and the applications and algorithms people are doing their things. We really need to get these communities together to solve this very challenging problem of building XR systems, AR, VR, MR systems that deliver the performance and quality that will truly change, how we experience the world around us and how we use computing. Okay, so so in addition, so those were all system level observations. We also did a lot of experimentation on the individual components, looked at the architectural aspects there, looked at what particular tasks are the ones that are stressing the system, did a deep dive on all of these components and really documented what's going on where, what's taking up time, what's taking up power, and so on. And again, we found that there's an abundance of tasks and there's no single task that dominates. And so if as system designers we're trying to figure out what to accelerate, it's very hard to do this manually, and we need automated techniques to do that. It's impractical to build an accelerator for every task, so we need to build shared hardware There's a diversity of compute and memory primitives, so we need more flexibility on the memory hierarchy, the communication interfaces, and all of these go back through, they permeate through the system stack, where the programming stack needs to deal with this, and the application stack needs to be aware of these trade-offs. And the algorithms are in flux, so we need to design programmable hardware. And finally, different algorithms have different QoE versus resource usage profiles. So we need to do end-to-end QoE-driven approximation techniques, and this is again a matter of research and cross-disciplinary research. So in brief, Elixir provides a very rich playground for systems research, and we have a lot of work going on with our collaborators, as well as others are using Elixir to do a lot of this type of research. I don't have the time to go into details for all of this, but I do want to leave you with some thoughts of the scale of work. So let me focus on the research first, and then I'll talk about the testbed and the consortium after that to wrap up the talk. So for research, we are looking at ways by which we can represent the heterogeneous parallelism that you have in these systems, that we will need in these systems. How do you represent this at the software level? There's a whole a bunch of us who are trying to make progress in this area. Okay, what is the programming stack for something like this? For hardware people, how do you automatically generate and select accelerators, and how do these accelerators work with each other? What is the software stack to use these accelerators? What is the communication interface between these accelerators? How do you do automated approximation selections? These are all collaborations we have with various groups within Illinois and outside of Illinois doing these projects. There's a clear case for cross-component co-design. Today, people who do scene reconstruction, for example, just focus on scene reconstruction. But how do we co-design? How can we improve the power, performance, quality profile of scene reconstruction by co-designing, by exploiting the opportunity that we can co-design with other upstream and downstream components now that we have a full open source system to experiment with? So a lot of work going on in this area. Other examples are co-designing eye tracking and foveated rendering. How do you do scheduling? So we built the runtime, but to do scheduling that can take that can give us, use the system as efficiently as possible is still a matter of research. So we have collaborations with others to build a scheduler that will efficiently meet the motion to photon latency requirements and other quality requirements of the system, and we already seeing better results than using off-the-shelf operating systems. So far, a lot of our work that I described is focused on a single headset, a single device. We are building systems now, moving from single device to distributed systems. So we already have support in Elixir to offload computation from the device to edge and cloud servers. And the next steps are we are looking at content streaming, multi-party AR/VR experiences, and we're excited about a collaboration with a group from CMU and their collaborators. They have a virtual meeting experience application that we are excited about putting on Elixir. That's a distributed application. And there are many, many more research use cases. There's a paper that was published using Elixir a few months ago on using eye tracking and holograms. There's groups doing work with Elixir on security and privacy, 360 video streaming. I talked about a multi-party AR programming stack, work on displays, on-sensor computing, metrics, and various XR algorithms that people are developing because, in different ways. Now that they have a full end-to-end system, you can do your algorithm development for SLAM or for scene reconstruction without really having to reinvent the entire system. You do your new SLAM and plug it into Elixir and see what you get from end-to-end performance point of view. For the Elixir testbed, also we have a lot of ongoing work. So this was so far I was talking about research. But now this is about developing the testbed itself, the one that's out there, open source testbed. Of course, we are adding new components, regularly. We are adding new implementations of current components in hardware and software. I talked about the offload, onload for edge devices and servers cloud. This is we are wanting to or in the process of building this onto the open source release. Lots of future work on content streaming, multi-tenant and multi-party experiences, edge and cloud server frameworks. We are working with applications people and end user to bring more and more end user applications, including middleware on top of Elixir. So there are large class of experiences that we can experiment with, creating and curating data sets and test stimuli, broadening hardware and software platform supported. So Elixir, I said, works on Linux right now, but we have an effort now to move it to Android as well. And of course, incorporating all of the research results that I talked about. So Elixir started as a project in my group, but we've now broadened it up, and we have an open consortium, as I said, with several companies and academics working with us. The goal is, again, to build a reference open source testbed that the community, both the research and development industry community, agrees on, where there's consensus that this is the testbed that we're going to use to compare research results, to do benchmarking of various systems, and to provide as an open testbed for whoever wants to do development on XR, so that they can focus on their place of interest and not have to worry about the rest of the system, and as well as building a community together. So in this regard, we will be starting or restarting open meetings for the consortium in January. That is the easiest way to get involved. So weekly meetings where people discuss various aspects of XR and the Elixir testbed, their experiences with Elixir, what they would like to see, etc. So right now, these meetings are with it's a single group meeting, but over time we are developing various working groups on various topics such as metrics, the interfaces, components, etc. And there is a plan developing to split the group into individual working groups that can then take on each of these individual aspects of the testbed and benchmarking strategy. So I invite you to get along, get involved, and help democratize XR research development and benchmarking, and use Elixir. We believe it's a rich playground for not just systems research, but also algorithmic and applications work and development. So you can send me an email or just join our Discord group. That's the easiest way to get a response from us. Okay, so that's all I have. Christine.
Fabulous. This has been so so great. I really, of course, it's exciting for us, the research committee specifically, and our community as a whole, focusing on the platforms. I've been an advocate for interoperability for many, many, many years, and there are many ways to get to interoperability, and one of those is certainly using open source and community projects like this consortium are critical, I think, and the members that you have in your consortium are just fabulous. So thank you for taking it this far already. Really, really pleased. And I look forward to the meetings resuming in January and to the future work. One of the things that you didn't bring up, but that is possibly a corollary to making a reference architecture widely adopted, is standardization. You mentioned OpenXR and the support of this specification, that this is a Kronos group specification. And I understand that the user interface pipeline at the at the runtime application seems like it's just at the at the interface between your orange block here and the XR applications would also include perhaps WebXR. That's another possible specification, the W3C immersive WebXR specification. And I wonder if you're looking at any other standards that could be implemented.
Yeah. Thank you for bringing that up. Yeah, so definitely WebXR is definitely something we want to look into and support. And as I said earlier, so far we've been mostly focused on single device, but now we are branching out into a more distributed space. And certainly WebXR is on our list of things to do.
Are there other specifications that you're looking at in addition, perhaps from other standards group or within Kronos?
So these are the two most the most obvious things to support right now. And if there's interest in other things, yeah, we would be happy to consider.
Okay,
but
so I have a
right now the way we see it is that, yeah, go ahead.
So the Kronos group over the last 6 months, since I don't know, March of this year, ran an exploratory group. That's a process that happens in advance of establishing a standards working group on the subject of camera and camera APIs specifically. And all that material is public. It's called the Camera API Exploratory Group. And there was just a charter that was voted, I think last week or, very, very recently. The Kronos board has to review it. And then I guess in the new year, there'll be meetings of that group. So that would seem like a really appropriate one for you.
Yes. In fact, so I'm glad you brought that up. So also, I should mention that we are part of the OpenXR group. So the idea is to be able to influence the OpenXR spec, as well as ensure that Elixir stays on track, because this is still an evolving spec. And there's a lot of work to be done. So I want to make it pretty clear that there's still a lot of work to be done on the OpenXR side as well, to ensure that systems like Elixir and XR systems get all the information evolving work, and we are very much involved in helping influence this. So I also want to point.
Sorry.
Yeah, and then before I get to the specific camera question, I also want to say that the OpenXR focus is here between the application and the system. What we are also trying to do through our consortium, a big focus in our consortium, which will eventually bleed into this external interface, is to build standardized interfaces for within the system. So today, for example, if you take a VIO or just a form of SLAM, and someone wants to design a new SLAM algorithm, right? And you want to use that with the rest of the system, right? There are no standard interfaces to connect SLAM to the entire system. Okay. And so what we are also trying to do, or a big part of what we are trying to do in our work, in the consortium work, is to standardize these interfaces as well, these internal interfaces. Cameras are a great point, because definitely we want to have standardized camera interfaces, and I'm glad you brought that up. Whether we build our own and standardize them, or work with Kronos, and perhaps the group you're talking about is the right one to work with that. This is a work in progress. So we're definitely interested, and a big part of the ILLIXR Consortium is to standardize all of these interfaces here. So maybe this is a better picture, right? This picture, right?
Mm-hmm.
So this entire DAG of communication, right? This is all developed by us, right? There's no standardization here, and we would like to standardize this. And for some of these components, that interface also bleeds into the application, right?
Mm-hmm.
And so this has to connect with OpenXR. It has to connect with the camera interface that you talked about, and how that connection happens is part of our ongoing work.
Okay.
So you will see that ongoing work on the ILLIXR Consortium interfaces is number 2 here.
Right. So another, I'll be happy to send this to you, and hopefully you could share it with the list. There's a specification. It's a framework architecture that was published a few years ago by the ETSI framework working group. It's an industry specification group that describes the modular components of an AR runtime. And I believe that it's also highly appropriate for your current project and this architecture to find ways to align the specification as it was defined by the ETSI ARF and this research pipeline. They serve different purposes, but one of the things that when we were working on the ETSI ARF framework, reference framework, what we encountered was that from the commercial side, these components, especially the perception pipeline on the left-hand side of your figure, but also the center one on visual, these components are, to my knowledge, always provided by a single manufacturer. They put these on a chip, and their whole value proposition is that it's not decomposed. Their whole value proposition is, just come and get this. It's all in one place, and it's all optimized. And that's kind of the opposite of what you're doing when you're decomposing. So can you talk about that?
Yeah. So are you talking about ESKI, is this Damien and companies?
Nope. I'd like to know about that. It's called ETSI, ETSI. It used to stand for European Communications Standards Institute, but they are not limited at all to Europe. They are one of the partners in 3GPP, and it is a standards body like many other SDOs. So it's a normative. Yeah.
Got it. Okay. So good question. So that's exactly right. That today this whole thing comes as a box, right? And our thinking is that if we want to democratize research and be able to compare systems and have a proper benchmarking effort so that we can so one of the reasons why computing from a systems perspective has flourished is along with building real systems, we also know how to measure the goodness of the systems. And so if you start all the way from Moore's law in hardware, right? Moore's law talked about system performance. Well, the original Moore's law talked about number of transistors, but it has been used to talk about how system performance doubles every so many months, and now Moore's law is flagging, and so we have to figure out new ways to measure hardware performance. And we've always known how to do that using standard sets of benchmarks and so on, imperfect as they may have been, but there's always been a way to compare systems. And that's what has led to competition and to
For sure.
Just an explosive kind of an ecosystem where there's clear paths, there's clear benchmarks to reach, right? You need to hit this performance metric, and that makes you better than so and so your system works out better.
Exactly.
In this domain, we are lacking all of that, right?
Yes.
There's no such standard accepted ecosystem, and that's what we are trying to change. And by keeping all of this closed, right? If we keep all of these components closed and look at them as a black box, we're never going to get there, because there's a lot of innovation that needs to happen in each of these things. Like I said, you know, without innovation across all of these algorithms, across the hardware, programming, compilation, runtime, algorithm application stack, we are not going to be able to reach where we want to reach in, you know, as quickly as we can. Plus, this is, if we don't think about opening this entire thing, this will continue to be the domain of a few companies.
That's correct.
And that was the other thing that happened with hardware, right? So hardware, you know, the ecosystem flourishes because now, you know, now there's many companies trying to build ML accelerators is the big thing now, but hopefully, you know, we'll get to these types of systems as well. And an open ecosystem is absolutely essential for that. So treating all of this as a black box is you know, hinders that. Now that's one aspect. The other aspect is that you know, you're not going to be able to do everything on your headset, as I said.
For sure.
You are probably going to want to offload some of this to the cloud, to an edge server, etc. So if all of this is treated as one black box, how do we do the innovation that looks at offloading some of this, right? How do we do the innovation that tries to build an end-to-end stack where we are you know, able to trade off network bandwidth and network latency with the quality here? You know, you do need to be able to attack these problems separately.
Oh yes, and I think, in fact, we're just at the top, near the top of the hour. I want to remind the people who are listening and our audience that the next 2 webinars, research committee webinars, are on related subjects. In particular, in February, we'll be hearing about research conducting at Duke University about exactly this decentralization and distribution of computational load, memory, data to device and edge devices, or edge services and nodes. So this is, of course, highly relevant to those who are interested in real-time performance and in 5G services, and how to make the systems less power consumptive, lighter, and reach all those other metrics that you had at the very beginning. Well, it's excellent to know of this work. Thank you very much, Sarita, for this exciting presentation, and good luck on continuing. I'm sorry that my audio is skipping out a little bit, but I want to say thank you very much, and I look forward to the next chapter. Okay, I'm sorry that the audio is not at the highest quality, but I'm going to end the webinar at this time. So it looks like I'm maybe back. Can you hear me, Surya?
Yeah.
Okay, I'm sorry about that interruption. I just want to say thank you again. This was excellent, and I look forward to hearing about the next chapter.
Thank you.
Happy holidays. Goodbye.
Bye.